All right.
Okay, awesome. Welcome back, everyone, to this week's seminar. And today we have Dr. Tristan Mullins. She's a cybersecurity professional specializing in side channel analysis, cyber physical system security, and supply chain integrity. She works as an R&D associate and signal processing engineer at Oak Ridge National Lab. Dr. Mullins received her PhD from South Alabama University in 2022, where she focused on developing novel defense mechanisms against channel attacks and made significant contributions to the adaptive security architectures. And today she's going to tell us about, again, side channels, using side channels for critical infrastructure protection. Um, Thank you for agreeing to give a talk. And yeah, whenever you're ready.
All right. Thank you for that intro. Let me get my screen shared, get my slides pulled up, and get them presenting. Okay. So, like she said, I'm going to talk to y'all about using side channels for critical infrastructure protection. This talk is it originally was focused toward researchers and how we can better bridge the gap between current curriculum and improving our workforce for addressing this issue and these opportunities within this field. But I've recently tweaked it a little bit to talk to students. I usually talk about this stuff in person, so it's more interactive. But maybe I'll just like ask myself questions and respond. We'll see how it goes. So we'll all figure this out together. So you heard a little bit about me a second ago, but I'll tell you some other things. I've been at Oak Ridge National Lab for 3 years now. It'll be 3 years this summer. I did both my undergrad and my grad degrees at the University of South Alabama. That's down in Mobile by the beach. I did computer and electrical engineering as an undergrad and then computing for grad school. So I've gotten a wide variety of hardware and software, but for my dissertation, I married the two together and I worked on developing a countermeasure for side channel attacks. I'll tell you a little bit more about that in a few minutes. I was also part of the Scholarship for Service program. So, this is a National Science Foundation funded scholarship program for people who are pursuing degrees and planning to work in cybersecurity. What that does is it covers your tuition and gives you a stipend to live off of. And that's for 2 or 3 years of your education. And then you work for a government funded agency for 2 or 3 years. That's how I discovered cybersecurity and national security research and the way I found Oak Ridge National Lab. Currently, I'm really involved in our workforce development group, which we call our National Security Sciences Academy. So that group focuses on relationships with universities and also in spreading awareness of what we do as far as national security goes at the lab, not only to other professionals outside of the lab, but also other people that might not work in the same area that we do. At Oak Ridge National Lab, you're really allowed to work on just about any project you want to. So when it comes to working on projects, we oftentimes will reach out to experts that don't necessarily work in national security. And that's a good way for them to learn more about how their science can help protect the nation. I've also founded the IEEE Young Professionals Affiliate Group for East Tennessee. And that's just another organization that our goal is to help bridge the gap between being an engineering student and being an engineering professional, and also excelling your professional career. So at the lab, I work in the Cyber Resilience and Intelligence Division. That's within our National Security Sciences Directorate. And we cover all kinds of different cyber physical research. So, cybersecurity, we secure critical infrastructure like the electric grid. I heard someone mention earlier Cymani. That focuses on securing manufacturing systems. We also look at vehicle security, and we have what was the world's first and fifth fastest supercomputers. They've recently been outpaced, but we have those high performance computing facilities on site, and we get to also do research with those as well. Um, So for what I'm going to talk about, I'm going to give you all some more background on side channels. I'll talk to you some about how I got involved in side channel research, and then I'm going to tell you about two projects that I've worked on at the lab to give you context for how this topic gets used when it comes to national security and critical infrastructure protection, and also how, as students, you can get more involved and learn more about this space. So, side channels. They are unintended information leaks. So, as an adversary, you can measure physically physically observable phenomena like power consumption, EMAG radiation, timing, all these things that we can't escape. We're all victims of physics. You can measure differences in those signals to derive information about what process is going on. This can happen in hardware or software. And oftentimes the target for these are cryptographic implementations. So you can do things like whenever a operation is being done using the secret key for a crypto algorithm, you can measure these things like power and timing and EMAG radiation and derive the bits of the secret key. So this picture up here shows some examples of a bunch of different side channel information that's out there to gather. And then this picture on the bottom shows an RSA modular exponentiation. What that means is a crypto algorithm does math with a key, and you can measure the power consumption of that device when it's doing said math. And the amplitude of the signal actually corresponds to the value of the secret key that's being used at that moment. I oftentimes relate side channels to like staying up too late when you're a kid at your house. How do you know that one of your parents are about to come upstairs and bust you for staying up too late? You don't open your door and watch for them. You listen for different clues. Like you can listen for footsteps and know what room someone might be walking in. You might look for light shining underneath the crack of your door to know if someone's up. Things like that. Those are side channels that tell you what the state of people in your house are in. What I did for my dissertation, well, first, the ability to do a side channel attack depends on the availability and the usability of a side channel. So there's currently not a single countermeasure that can eliminate all side channel leakage. So designers need to layer multiple side channel countermeasures in order to protect against these types of attacks. Some concepts for these in like a FPGA or an SoC. Think of this as a device that has a hardware and a software component. You can do things like location distribution. With that, you take whatever the target hardware might be and you have either multiple instances of it or one instance that moves around in the hardware. That reduces the availability of the side channel because the adversary does not know exactly which area to target. Another option might be hardware software partitioning, where we take a program and we chop it up and we say, okay, we're going to execute some of this in software, and then we'll take our data and send it over to hardware and run it through a circuit and back and forth like that. That reduces the usability of the side channel because hardware and software have different side channel properties. The adversary no longer has a consistent side channel behavior that they can use to do their attacks with. Okay, now here's the slide that I thought I was almost at. So for my dissertation, what I did was I created a circuit variant moving target defense for side channel attacks. That's a lot of fancy words, but essentially what it means is I took the target hardware for an AES algorithm and I moved it around in hardware. So think of it like the shell game where you take a ball, you put it underneath a cup, and you shuffle it around and then you lose your money. That's basically what we're doing with the target hardware. We're moving it around to make it harder for an adversary to be able to run their attack because they have an ever changing target. Not only did we shift things around, we also, every time this target hardware moved around, we changed up its structure. So we used something called a program encryption toolkit to generate a bunch of different versions of the same circuit. So essentially, you would get with input X, you would get out expected output Y, but all the gates that it was passing through would vary in size and type. And so that changed up things like the timing and the power consumption and also the EMAG signatures that were coming off of this. So we're changing it in a couple different ways. And that reduces, like we looked at just a slide back, the usability and the availability of a side channel. Okay, we're done with the background. So side channels, they're oftentimes considered attack vectors. But whenever I started working in national security, I had to think with a white hat and think, how can these things be used for good? Turns out they are used for good. A lot of times, side channels are used in anomaly detection. It's still a growing field, but you might hear it referred to as something like out of band sensing. So, measuring these different physical characteristics can be used to figure out if something's going wrong within a system. So, in the context of critical infrastructure, this allows for owners and operators to make to monitor without interfering with real-time constraints. So we want to have good uptime, a good response time, and so these things are passive and don't interrupt the normal operation of the system. They can also be retrofitted onto legacy systems with something like out-of-band sensing. That's important in this critical infrastructure where some of these devices are hard to update, hard to get to, and it would be tough to swap them out and have something new put in place. Having something that you can bolt on for security purposes is awesome. So, what we need are designers, security professionals, researchers, and even students to be aware of not only the threats that side channels introduce, but also the opportunities for leveraging them for out of band sensing and securing these critical infrastructure systems. So, how do we do that? How do we prepare these people? The way we close the gap um, is by leveraging things like student programs. So, a lot of these concepts, oh, here we go. We need to give students hands-on opportunities to develop these skills that we need in our workforce that might not be widely available at the university level. So I was able to use my marriage of hardware and software background, but a lot of times those skills or those courses that teach those skills either aren't available in certain curriculums or they are available, just maybe not for people who are more cybersecurity focused. There's you can pick and choose different courses and topics from all over universities and make your perfect degree, but that's not really possible. You need to do the best with what you can, and the best way to address this is by getting involved in the fields that we're interested in, like critical infrastructure protection. The best way to figure out what you don't know is maybe try out an internship or something where you can actually see what's being done and address your own gaps and figure out what there is to further develop. These topics can be things like OT security, industrial control systems, signal processing. That's something that oftentimes doesn't get addressed in computer science, and also hardware protocols. All of these things are useful and they're taught, but they're not necessarily all taught to the people that wind up working in these fields. So the way I went about this was I had a group of interns last summer. We worked on critical infrastructure protection. All of them had different backgrounds, but they all had the opportunity to design their own research and design their own test bed and actually put these skills or try test out these skills sometimes for some of them for the first time. And for some of them, they had a lot of skills that were applicable, but might not have seen them in a security context in this way before. So, what they did was they designed an access control test bed. We bought it off of Amazon. It's a simple badge reader, control board, and lock. And they designed it, put it together, and then ran attacks against it and investigated countermeasures. So they did 3 different attacks. This Pelican Case has actually outlived this project, and now it's our traveling demo. We get to take it to universities and job fairs and show people a little preview of what we get to do every day at the lab. So the first thing they did was a TCP replay. So this board with this red square on it in the middle, that's the controller for this whole badge reader test system. They were trying to see, okay, if I were an adversary who didn't have a badge to get in, how would I bypass a legitimate badge swipe? When you're configuring the system, you plug in with that Ethernet port into a computer or a workstation that has the configuration software. That's where you register certain badges and say, okay, Jeff has access to this door, Todd has access to that door, and we get it all set up and everything runs all fine and dandy. Well, there are some additional features. One thing you can do is you can just simply send a command to unlock the doors. Uh, One way that that might be useful is, say you have a maintenance crew coming in and you don't want to give them all temporary badge access. If they're only coming in once or twice, you can just unlock the door and let them in. Well, they said, can we intercept that? So they intercepted the packets between the control software and the control board, and were able to take the unlock packet, put it in a script, and as long as they have access to that Ethernet port, they can run their Python script and unlock the door. Some ways that you might be able to protect against this that they looked into are things like uh, having preventing man in the middle attacks. So having something that changes or rolls over whenever as time passes. Having some sort of detection for previously played packets would work, and also having some kind of encryption over this traffic would also help prevent these kinds of attacks. The next thing, they used a Flipper Zero. You might have seen videos about the Flipper Zero on like YouTube or TikTok or whatever. It's basically a red team hacker tool. It has all kinds of functionalities, but we only leveraged a couple of them in this project. But what you can do is you can actually capture and clone RFID tags or cards. So with this, let's say Jeff left his badge sitting at the counter when he ordered some coffee. Someone can come up with a Flipper Zero, clone it, and then use it instead of an actual badge and unlock the door. Ways we might protect against this is where the interaction part comes in. I usually ask people to tell me, and that's also where I get more ideas to do more research, is sometimes I hear things that I haven't thought of before, but I'll just share them with you. We can do things like rolling codes. That's something like what your car key fob or your garage door opener uses to keep you from being able to replay your neighbor's garage door opener or key fob. You could also have something like two-factor authentication, where you have to also punch in a PIN to unlock a door. Um, and then, oh, I already said something that changes every time. Okay, that's it. Let's go to the next one. This is the coolest one. So this little thing in the red square, it's about the size of a postage stamp. It was the initial inspiration for this project. It's called an ESP key. If any of y'all have heard of DEF CON, it's a hacker conference. It was they had a talk called Badge of Shame about 2 years ago where they talked about the ESP key and then a newer, bigger, better, badder version of it for another protocol. That talk was a big inspiration for this project. Well, what the ESP key is a man-in-the-middle device that you can buy online, and it doesn't require any extra tooling. You just punch it down onto those wires that are going into that badge reader. And what it does is it intercepts all the traffic. Every time you do a badge swipe, it's got it. It puts out a Wi-Fi signal, and it has its own little web server that you can see in this top right corner over here. And you can see the badge number in plain text in here. You can also replay any captured badges. They'll populate in a list, and you just click transmit, and it will resend that packet to the control board and unlock the door. You can also do denial of service with this thing, where it will block all the traffic coming from that badge reader trying to get to that control board. So, oh, there you go. There's the denial of service. Our little light turns red and the lock doesn't unlock. So some other ways that we might protect against this are similar to the things that we talked about previously. Having some sort of detection for replayed packets, maybe having two-factor authentication, all that good stuff. Better physical security would also be good. If an adversary doesn't have access to these wires and they can never put their ESP key on the line, right? That's all great and wonderful. We wanted to look into, can we detect if one of these things were put in our critical infrastructure? So this applies to more than just badge readers. Hardware implants are a threat all over the place. If we are preventing certain critical infrastructure from being able to do what it does, we run into all kinds of problems, right? A lot of times we have safety mechanisms that are controlled by simple pieces of hardware. If an implant gets, or a hardware implant gets introduced that can cause damage, we want to know about it before it actually runs its attack. So we looked into, can we use side channels to figure out if this thing is on the line? And so one thing that we noticed is that it consumes what's called parasitic power. What that means is it doesn't have to have its own power source. It can use the power supply for the badge reader. Well, when it does that, the badge reader overcompensates and draws additional current, and you can measure that. So if you were to have a current probe or some sort of power monitor for that badge reader, you would notice a difference when the ESP key is on the line versus not on the line. That's something that my students found out over the summer when doing their research. They found that out at the end of the summer, and then everyone left, and we still had cool stuff that we found that we wanted to take further. But an internship is only so long. You can only change the world so much in your 10 weeks that you're somewhere like Oak Ridge National Lab. So what did we do? We started an Ensure project. So Ensure is a program that links government agencies like DoD and DOE labs to CAE schools, so Center of Academic Excellence schools, for one semester. The students take a course for course credit, and researchers at these institutions propose problems for these students to work on. You get matched up, and then you have a mentor from a lab or DoD for your project that you're working on at your school all semester. The reason we wanted to do an Ensure project was to address some of these limitations of this method of sensing this ESP key. So one of the limitations is we were only able to detect it when it was consuming parasitic power. We were interested in seeing, well, what if it's powered by an external battery? Do we have options for detecting this ESP key? Another thing is measurement scalability. So when you have something like a building, you usually don't have only one badge reader. There's usually a ton of them. So having measuring at the badge reader level, putting our sensors there, makes this really difficult and really costly to scale up. So that was the thing that we were going to research first, is what are our options here? How do we make this more affordable and more feasible for a larger system? Something that doesn't fit inside of a Pelican case. Already said all that stuff. Okay, so my Ensure team was from my alma mater, South Alabama. They had students that were experienced in side channel analysis. And one of them was one of my interns that had worked on this project before. So what they did was they developed their own test bed. So I couldn't send them my OTAC badge system in a case. They had to make their own. So what they did was they used a BeagleBone Black as their normal system, and it would talk to a laptop. And then their hardware implant was a bus pirate. And that is what they were trying to detect. They wanted to see, can I use side channels to know if a bus pirate has been intercepting my data between my BeagleBone and my laptop, or is it everything as normal? So what they had to do here was design their own experiment, design their own test bed, and figure out, okay, what do I measure? Where do I measure it from? And then also, what do we do with this data? It's a lot noisier than that RSA signal that I showed y'all earlier. They couldn't just look at it and be able to tell. They had to have some signal processing. So they decided to go with a machine learning application for their post processing. And all of this was up to the students to learn more about and decide. What they did was they measured both the power supply going to the beagle bone, and then they also looked at EMAG radiation. This was something that we didn't do in the OTAC project before. They measured across 5 different locations. There's a 5-volt pin, PMIC, which is the power management integrated circuit, the UART transmit and RX pins, an oscillator, and also a processor. So they compared measurements with and without that hardware implant across all these different locations. What they found was that the power measurements were noisy. They had accuracy just under 90% when it came to detecting this hardware implant. Ways we could improve that might be just having better trace collection, so improving their signal capturing skills. When they did EM, though, they compared all the locations, and the one over the power management circuit was the best. They were able to get over 90% accuracy when it came to detecting this implant. Why that is could be that the power management circuit is used for things like power smoothing. If we think back to that example with the badge reader, and how the reason we were able to use side channels to detect the implant was because of the overcompensation that we could see in that power consumption. With this, we were able to see that same behavior just at a different location. So ways we would look into this in the future would be maybe looking into, instead of doing post-processing, would be, can we do anything in real time? Can we develop some sort of anomaly detection system and signal processing unit that could give us our flags in real time? That would make the system much more realistic. Another thing would be check out different targets. So with the beagle bone, that power management circuit was something that we didn't have when we looked at the ESP key, or we didn't know was available. Having targets like that would make this much more scalable. If we were able to have something similar to that power management circuit that we could observe at the control board level, that would mean if control boards handle, let's say, 20 doors, that would mean we would only need 1 sensor for 20 doors instead of 20 sensors. There are downsides to that. We will introduce more noise. It might be a lot tougher to find our anomalies, but that's just all part of the research, is refining and revisiting and trying again. Another thing, and this might be an address or a answer or a way to address the noise problem, would be, can we do side channel based fingerprinting of operations for anomaly detection? Let's say we have a more complex system. We're not just detecting hardware implants, but we're trying to detect a very specific malicious behavior. Could we say we have a microcontroller and it's only supposed to do 4 different things? Can we fingerprint those 4 different activities using side channels and be able to throw up an anomaly flag when we detect something that isn't in those 4 categories? That would be awesome. And then the last thing would be, can we use this beyond hardware implants, like with the behavior detection and the behavior identification? There's all kinds of ways to take this research. And all of these ideas came from the students, and these were students that hadn't worked with critical infrastructure before. So it's been a great learning process. We're hoping to continue this work with another INSURE project in the future. But the moral of the story is, and this is where I wrap up, is there's lots more to explore in this realm of side channels for anomaly detection. There's a lot of untapped applications that we need to research. The way we start figuring out all these uses is innovate and educate. We need to use student programs to introduce students to these topics, because you might find out that if you as a student join these, you might find out that this is the perfect area for you. And you might not have an opportunity to figure that out otherwise. Get involved in get involved in these education programs and these internship programs. Not only is it beneficial to the students, but also to us as researchers. It's the best way for us to develop a niche workforce. If we want people that we're hiring straight out of school to be aware and be experienced in these certain areas that we research in, our best bet is to offer internships where these students work on these projects, give lectures at universities like we're doing here now, where we actually talk about these subject areas. It's mutually beneficial. If you, this is my sales pitch, if you want to get involved in one of our education programs, check out education.ornl.gov. We have opportunities year round from high school all the way up post grad and for faculty to come hang out, come work on projects with us. It's mentor driven. So our researchers are the ones who are going through the application pools and finding people and designing the projects for people to come and work on throughout the year. So everything that you would get to do is very relevant to our missions at the lab. There's my contact info. If we'll go into questions, but if you have anything else that you want to ask me later on, I can drop my email in the chat. I'm always open to having conversations. I am extremely open to helping out with things like thesis and dissertation committees. That's something that researchers are a great fit for, is to help advise your research that you're conducting currently before you go out into the working world. So feel free to ping me on any of those things, and we can open it up to questions now.
Thanks, Tristan. Yeah, if you guys have any questions, feel free to put them either in the chat box or in the Q&A box.
Let me see. Okay, no open questions.
Yeah, let's maybe wait for a couple of more minutes for still no questions.
All right.
Hey, Tristan.
Yeah.
I have to admit, I've never heard of a bus pirate. Can you tell me a little bit more about that?
So we were using it in a very simple way, but it's another sort of like hacker tool that you can use to intercept data that's being sent between two devices. I haven't used it a ton, so I'd recommend checking it out. The best way to learn more about it is probably to watch like someone do
Yeah.
a hacking project on YouTube or a blog
Absolutely.
post or something like that. But yeah, we weren't using it to its full capability.
Sure. Yeah, that's something that's my first time. Like, I got to go on YouTube and see how they use it. So pretty interesting.
Yeah, you can. A lot of times, people will make little devices to intercept communication, so they can do things like reverse engineer a protocol or something like that. Learn more about the system. It's not usually used for what we were doing it for, but there's all kinds of cool ways and probably things that I've never even heard of that people use these things for.
Cool.
Okay, well,
Okay,
it
if
seems
there are
like
no
we don't have any questions, which is all right with me. Feel free to shoot me an email if y'all do think of any questions. Yeah, I don't think I have anything else to
Great.
add to that. I've said it all.
Okay, well, great.
Thank you,
Well,
Tristan. Thank you
yeah,
so much.
thank you so much. We really appreciate you joining us here.
Andrew jumped in the chat. He was one of my interns last summer that worked on that OTAC project and designed the test bed. So thanks
Oh,
for coming.
great. All right. Thanks a lot.
Okay,
Appreciate
awesome.
it.
Thank you so much.
Take care.
Bye.